Hi guys, and welcome to this tutorial where we're going to be trying something a little bit different, which will be looking at specific topic questions from different exam boards. And today we'll be starting with complex numbers. So watch the video through to the end, and if you like this style of video, just let us know in the comments below so we can make more videos like this. Okay, let's have a look at this question. So we're given this function f of z is equal to z to the power of 4 plus az cubed plus 6z squared plus bz plus 65, where a and b are real constants. Given that z is equal to 3 plus 2i is a root of the equation f of z is equal to 0, show the root of f of z is equal to 0 on a single argand diagram. Okay, so I'm just going to allow you a few moments to pause the video to have a go at this question, and when you come back, I'll show you the solution. So in this question, we're told that z is equal to 3 plus 2i is a root of the equation f of z is equal to 0. And we've seen in previous tutorials that the complex conjugate of z, 3 minus 2i, would also be a root of the equation f of z equals to 0. Now by the factor theorem, this means that z minus 3 plus 2i and z minus 3 minus 2i are both linear factors of the equation f of z, and if we multiply these together we get the following. So let's first expand out the brackets inside the square bracket. Expanding this bracket we get z minus 3 minus 2i, and if we expand out the curved brackets for this linear factor we get z minus 3 plus 2i. So just be careful when you're expanding out the brackets, and if we multiply the brackets we get the following. Z times z is equal to z squared, z times minus 3, which is equal to minus 3z, z times 2i, which is 2zi. Multiplying negative 3 by z gives us minus 3z, minus 3 times by minus 3 gives us positive 9, minus 3 times 2i is equal to negative 6i. Multiplying negative 2i by z gives us negative 2zi. Multiplying negative 2i by negative 3 gives us positive 6i, and multiplying negative 2i by 2i, well, I times I is I squared, which we know is equal to negative 1, and multiplying negative 1 by negative 2 times 2 would give us positive 4. Okay, hopefully you should see from this expression that there will be cancelling of terms. Negative 6i and 6i would cancel, and we'd also get cancelling of the terms 2zi and negative 2zi. And simplifying the remaining terms, we get z squared minus 6z plus 13, which is a quadratic factor of f of z. Okay. We could have also worked out this quadratic factor by using what we know about the roots of a quadratic polynomial of this form. Az squared plus bz plus c is equal to 0, where the sum of the roots is equal to minus b over a, and the product of roots is equal to c over a, where in this case a would be equal to 1. And you would use these results to find b and c. But given what we've just worked out, we can say that f of z, which was given as z to the power 4 plus az cubed plus 6z squared plus bz plus 65, is equal to this quadratic factor z squared minus 6z plus 13 multiplied by some other quadratic factor z squared plus cz plus d, where c and d are constants that we need to find in order to work out the remaining roots of this polynomial f of z. So by equating the coefficients, starting with the constant terms of this equation, we get that 65 on the left hand side is equal to the only constant term that you would get by multiplying these two quadratic factors, which is 13 times by d. Dividing both sides by 13, we get that d is equal to 5. So let's just update this quadratic factor. We can find the constant c by equating the coefficients of the z squared terms on both sides of the equation, giving us the following. On the left hand side, the z squared term would be 6z squared, and we would get the z squared terms on the right hand side by multiplying z squared by 5, which gives us 5z squared, minus 6z multiplied by cz gives us negative 6cz squared, and multiplying this 13 by z squared gives us 13z squared. Okay, so assuming that you are aware of locating coefficients of terms in an expansion, then this is the result you would get for the z squared terms. And if we simplify the right hand side, we'll get that 6z squared is equal to 18z squared minus 6cz squared. And equating the coefficients, we get that 6 is equal to 18 minus 6c. Subtracting 6 from both sides and adding 6c to both sides, we get that 6c is equal to 12. And dividing both sides of the equation by 6, we get that c is equal to 2. So now we've found all the coefficients of our quadratic factor. It follows that z squared plus 2z plus 5 is a quadratic factor of f of z. And so we can work out the remaining roots of f of z by solving the equation z squared plus 2z plus 5 is equal to 0, which can be solved using the quadratic formula or by using a calculator. Either ways, you would get the roots z is equal to negative 1 plus 2i or negative 1 minus 2i, which you would expect as it's the complex conjugate of this root. And so now we have all the roots, 3 plus 2i or 3 minus 2i, which were the roots we saw earlier. We can now sketch these on the Argand diagram. So as you should be aware, the Argand diagram illustrates the real and the imaginary part of a complex number. And so starting with the first root 3 plus 2i, it would look something like this, going 3 units to the right on the real axis and 2 units up on the imaginary axis. The other root, its complex conjugate, would be a reflection of this root in the real axis. This root negative 1 plus 2i would look like this, going 1 unit to the left and 2 units upwards. And this root, its complex conjugate, would be a reflection in the real axis. And don't forget to draw arrows for complex numbers on the Argand diagram. Okay, let's have a look at the next question. So the first part of the question says express minus 3 plus root 3i in the form re to the I theta, where r is greater than 0 and theta is between negative pi and pi. So I'll leave it to you to pause the video to have a go at the question, and when you come back I'll show you the solution. Welcome back. So in this question, we've been asked to express this complex number in exponential form re to the I theta, where r is greater than 0 and theta is between negative pi and pi radians. So if we let z be equal to negative 3 plus root 3i, we can draw this on the Argand diagram as follows. So this black line represents the complex number z, and we've called the acute angle between the complex number and the real axis alpha. So from the diagram, we can see that we can find r, which would be the length of this line, using Pythagoras. And therefore r, which is also the same as the modulus of z, is equal to 3 squared plus the square root of 3 squared, all square rooted. This is equal to the square root of 9 plus 3, and therefore r is equal to the square root of 12. Theta is equal to the argument of z, which is an angle between negative pi and pi radians. And on the Argand diagram, theta would be this angle here. We can work out this angle theta by first working out the acute angle alpha and subtracting it from pi radians. So using SOHCAHTOA to find alpha, we get that alpha is equal to tan inverse of the square root of 3 over 3. Now, bearing in mind that this is a non-calculator question, we can work out this value by first of all noticing that if we multiply the top and bottom of this fraction by the square root of 3, we get that this is equal to tan inverse of 1 over the square root of 3. And this is super useful for us since 1 and square root of 3 form the sides of the special 1, 2, root 3 triangle. And since tan of an angle is equal to the opposite over the adjacent, the side of length 1 would be opposite to the angle alpha, the side of length square root of 3 would be adjacent to the angle alpha, and the other side would be the hypotenuse. Now if you remember the angles of the special triangles in radians, then great, but I usually remember them in degrees as 30, 60 and 90 degrees. And since alpha is the angle opposite the smallest side, it must be the smallest angle, and therefore alpha must be 30 degrees, which is equal to pi over 6 radians, okay? We can now work out theta, the argument of z, by doing pi minus pi over 6, giving us 5 pi over 6, which is an angle between negative pi and pi radians, okay? And therefore, we can express the complex number z in exponential form as the square root of 12 times e to the power of I 5 pi over 6. The next part of the question says, let the roots of the equation z cubed is equal to 3 plus root 3i be u, v and w. Find u, v and w in expressing your answers in the form r e to the I theta, where r is greater than 0 and theta is between negative pi and pi radians. So again, I'm going to leave you with a few seconds to pause the video to have a go, and when you come back, I'll show you the work solutions. Welcome back. Now, given that we know the modulus and argument of this value, we can rewrite this equation in modulus argument form. Z cubed is equal to the modulus, the square root of 12, multiplied by cosine of the argument 5 pi over 6 plus I sine of 5 pi over 6. And using de Morgan's theorem, we can find the roots of this equation by taking the third root of the right hand side, which would mean raising the modulus to the third root and multiplying the argument plus 2 pi k, where k is an integer, by 1 over 3. And here I've just written the square root of 12 as 12 to the power of a half, which would make it easier to work out the new power. So when we sub k is equal to 0 into this equation, we get one of the roots. Z is equal to the sixth root of 12 multiplied by cosine of 5 pi over 18 plus I sine 5 pi over 18. And this is a root because our argument lies within the range. Subbing in k equals 1, we get the solution z is equal to the sixth root of 12 multiplied by cosine of 17 pi over 18 plus I sine of 17 pi over 18. And this also works as a solution because the argument again falls within the range. If you think about these values being multiplied by pi as fractions less than 1, then hopefully it's easier for you to see that this value is less than pi and therefore falls within the range. If we try k is equal to 2, we would get an argument of 29 over 18 pi. And since 29 over 18 is greater than 1, then multiplying by pi would give a value greater than pi, and therefore it would fall outside this range and cannot be taken as one of the solutions for this equation. So let's try when k is equal to negative 1. Well, when you sub k is equal to negative 1 into this equation, we get an argument of negative 7 pi over 18, which does indeed fall within this range, negative pi to pi radians, and therefore works as one of the solutions. And so we can write these roots in exponential form as u v w is equal to the sixth root of 12 times by e to the power of I 5 pi over 18, which was the argument of the first root when k was equal to 0. The sixth root of 12 times e to the power of I 17 pi over 18, the argument when k was equal to 1. And finally, the sixth root of 12 times e to the I negative 7 pi over 18, which was the argument when k was equal to negative 1. Okay, let's have a look at the next part of the question. On the Argand diagram, u, v and w are represented by points capital U, v and w respectively. The first part asks us to find the area of the triangle UVW. So I'll leave you with a few moments to pause the video to have a go at this problem. When you come back, I'll show you the workings. Welcome back, guys. So in this question, we're told that the roots that we've just found, u, v, w, and I'll just write these roots here. Well, these roots are represented by the points capital U, v, and w on the Argand diagram. So let's sketch these points on the diagram. So the point u will be roughly around here, Okay, since the argument is 5 pi over 18, which is less than 9 pi over 18, which would be pi over 2, it would lie in the first quadrant. The point V would lie in the second quadrant, as 17 over 18 is very close to 1, and therefore this value would be closer to pi. Okay, and lastly, the point W would lie in the fourth quadrant, as it's the only negative argument, which we would draw clockwise from the positive real axis. And by inspection, 7 over 18 pi is less than 9 over 18 pi, or pi over 2, and so would lie in the fourth quadrant and not the third quadrant. Okay? Now, since there are 3 roots, we've seen in previous tutorials that these roots will be spread out evenly around the circle of radius r, which in this case is the 6th root of 12, and the angle between each root is equal to 2 pi divided by the number of roots, which in this case is 3. And this is how we get the 2 pi over 3. Now we need to find the area of this triangle, UVW, and you should notice that there are 3 congruent triangles within this triangle, UVW. Now if we choose any triangle, say this one, since we have the length of 2 sides and the angle between them, we can find the area using the formula. The area of a triangle is equal to a half AB sine C, where A and B would both be equal to the 6th root of 12 and C would be equal to 2 pi over 3. Okay, and so subbing these values into the formula, we get that the area of UVW is equal to a half times by the 6th root of 12 times by the 6th root of 12 times sine of 2 pi over 3. But since we have 3 congruent triangles within UVW, we need to multiply this value by 3. Now we need to work out the exact value of sine 2 pi over 3 without a calculator. Using the quadrant diagram, you should be able to see that sine of 2 pi over 3 would be the same as sine of pi over 3, and pi over 3, or 60 degrees, is a special angle, one of the angles in the special 1, 2, root 3 triangle. And since we know that sine of an angle is equal to the opposite over the hypotenuse, it follows that sine pi over 3 is equal to root 3 over 2. Okay? And therefore the area of UVW is equal to a half multiplied by the 3rd root of 12, which we just get by multiplying the 6th root of 12 by the 6th root of 12. We just add the powers, multiplied by the square root of 3 over 2, which we just got from the sine 2 pi over 3, multiplied by 3, which is equal to 3 root 3 over 4 times the 3rd root of 12 units squared. Okay, let's have a look at the final part to this question. By considering the sum of roots u, v and w, show that cosine of 5 pi over 18 plus cosine of 7 pi over 18 plus cosine of 17 pi over 18 is equal to 0. Okay, so welcome back. Now we've been asked to consider the sum of roots and prove that it satisfies this equation. Now just for your reference, the roots u, v and w that we found were roots to this equation. Z cubed is equal to negative 3 plus root 3i. And if we rearrange this equation, we get that z cubed plus 3 minus root 3i is equal to 0. Now we've learned from previous tutorials that if we have the following cubic equation of the form az cubed plus bz squared plus cz plus d is equal to 0, then the sum of roots, which we can just call alpha, is equal to minus b over a. Now if you look at this equation, it's just a cubic equation of this form. But here we have that a is equal to 1 and b, well, there is no z squared term in this cubic equation, and therefore b is equal to 0. And so it follows that the sum of roots that we found for this equation, u plus v plus w, must be equal to 0, as minus b over a would be equal to 0. To work towards proving this equation, we can rewrite what we've just found in modulus argument form. Since the 6th root of 12 is a common term on the left hand side, we can factor this out, which then allows us to divide both sides by the 6th root of 12. And now if a complex value is equal to 0, Well, this means that both its real and imaginary parts are equal to 0. Perhaps you'll see this a bit more clearly if we were to write this as 0 plus 0i. Equating the coefficients, you'll get that the real and the imaginary part are equal to 0. And based off of the equation that we're trying to prove, we can write that the real part of this complex number is equal to 0. And we're almost there, as we get cosine of 5 pi over 18 plus cosine of 17 pi over 18 plus cosine of minus 7 pi over 18 is equal to 0. The only problem is this negative 7 pi over 18. But you should already be aware that cosine of x is equivalent to cosine of negative x. And I like to think about this visually. So assuming we had a function f of x, then the function f of minus x would be a reflection of f of x in the y-axis. So if we draw the graph of cosine of x, then cosine of minus x would be a reflection of this graph in the y-axis. And if you reflected this graph in the y-axis, hopefully you would see that you would get exactly the same graph again, which makes it easier to see why cosine of x is equivalent to cosine of negative x. So this must be equivalent to cosine of 7 pi over 18. And therefore we get the equation cosine of 5 pi over 18 plus cosine of 17 pi over 18 plus cosine of 7 pi over 18 is equal to 0 as required. Okay. So I hope you found that somewhat useful for your revision. Keep up the good work, and I'll see you in the next tutorial. If you like this video, please give us a thumbs up, leave your comments down below, and subscribe to this channel so you'll be the first to know when we release our next videos.